Okay, in this video, I'm going to just explain a little bit more in depth about some Bronsted-Lowry reactions that we've either talked about in class or that kind of show up in your practice packet. The example that we did in class was, let's see if I can get my pen to work here. There we go. The reaction between ammonia and H3 and water. And the products of this reaction were the hydroxide ion and the ammonium polyatomic ion as well. And all you really need to know how to do for the test is how to identify which one of these is the acid and the base and which one of these is the conjugate acid and the conjugate base. And that's kind of explained. We talked about that in class, and that's explained, I think, in another video. But some of you may have questions that go a little bit deeper than just labeling those. And so in this video, I kind of wanted to show you what's going on as far as how that proton is transferred from water to ammonia. And they give you an example from the practice packet that a lot of you have had questions about. So in order to explain kind of why this one of these hydrogens leaves the water and comes over here and joins up with ammonia to form the ammonium ion, you have to kind of go back and think about drawing those Lewis dot structures and knowing the number of valence electrons that are around these atoms. So I'm going to start by drawing the Lewis structure for ammonia. So we've got our nitrogen is going to be our central atom, remember, because it makes the most bonds. Nitrogen has the ability to make 3 bonds, and it also has a non-bonding electron pair. And so let's go ahead and say, so it's got 5 valence electrons, 1, 2, 3, 4, 5. Okay, so we see we've got our non-bonding electron pair up here, and then we've got a hydrogen here, and remember that each one of these hydrogens is contributing 1 hydrogen to this shared electron pair. And here's the last hydrogen. Okay, and so here's what ammonia looks like. And then we've also got water, and here oxygen, remember, is going to be the central atom, and it has 6 valence electrons. So 1, 2, 3, 4, 5, 6, and 2 hydrogens, each contributing 1 shared electron. All right, so here's what these 2 molecules look like. We put ammonia in this aqueous solution. What ends up happening is water ionizes to form hydrogen ions, which, remember, this is literally just a proton. So what's happening here is this hydrogen is taking off and it's leaving behind its electron. So it's only the nucleus of this hydrogen atom that's leaving, and we end up with a hydroxide ion. And so I'm going to go ahead and draw the valence electrons around this oxygen again, just to kind of illustrate what's going on. So we've got these 2 non-bonding electron pairs, right? That's this pair. That's these 2 pairs right here. And then we've got this 1 electron from oxygen, 1 of them from this hydrogen. That's forming a bond there. And then normally, if we were drawing a normal Lewis structure, oxygen would have this 1 more place down here where a bond could form. But when this hydrogen left, it left behind the electron it was sharing with that oxygen. And because this has that extra electron now, this whole group of atoms becomes a negatively charged ion called the hydroxide ion. Okay, so now we've got a positively charged hydrogen, a negatively charged hydroxide ion, and we've also got this ammonium ion right here where we've got our 2 non-bonding pairs and then our 3 hydrogens. And this hydrogen ion, or this proton, is attracted to this non-bonding electron pair on ammonia. And you might be asking, well, why doesn't it just go back and form another water molecule? And it may sometimes, but the reason it's attracted to this non-bonding electron pair on this nitrogen is because nitrogen is slightly less electronegative than oxygen. And so it's going to be holding on to these electrons just slightly less than the oxygen is holding on to these electrons right here. And so it's easier for the hydrogen to come over here and attach itself to this ammonia ion. And then that's where we get, after this interaction takes place, we have hydroxide with this extra electron right here and a negative charge. And then we end up with ammonia. And the reason why the ammonium ion has a positive charge associated with it is because we added that proton. Remember, this hydrogen did not contribute any additional electrons. So there's an imbalance in the number of electrons around this or in this molecule to protons. And so we have one more proton than the number of electrons. And so we have a positive charge. Okay, so again, this is not, the only thing you have to know how to do for the test is label, the compounds in the formula as acid base, conjugate acid, conjugate base. But for those of you who want a little bit more in-depth explanation about what's going on, here it is. And there is one more example that I wanted to show you, or at least talk about, and I'm going to just go ahead and kind of squeeze that down here. So in your practice packet, there's a section that asks you to circle the atom that the acidic hydrogen is going to be attaching to. And one of the compounds it gives you is CH3 and H2. And you have to circle one of those four, one of those three elements in there, all right? And in order to figure out where this acidic hydrogen is going to go, we have to look for a non-bonding electron pair, just like we did over here. And so I'm going to go ahead and I'm going to just make a note of how many bonds each one of these elements in this formula can make. So carbon can make 4 bonds, hydrogens can make 1, nitrogens can typically make 3 bonds, and there you go, there's 1 for hydrogen. So most of the compounds that we've dealt with, that we've drawn Lewis structures for, have a single central atom. However, this compound right here, any of these elements that form more than 1 bond are going to be considered central. So we've definitely got carbon and nitrogen that are going to form the central portion of this molecule. And then as this formula is listed, it's got these 2 hydrogen groups separated from one another. It's not just carbon, nitrogen, and then 5 hydrogens. So anytime we have an expanded formula like this, the hydrogens that come directly after, the element that makes the more bonds are attached to that element. So in this case, we've got these 3 hydrogens being attached to this central carbon. So carbon has a bond with a hydrogen here, a bond with a hydrogen here, and a bond with a hydrogen here. And so you can see that carbon has all 4 of its bonds filled. So there's no non-bonding electron pair around carbon. So that proton is definitely not going to attach itself to carbon because it doesn't have anywhere to go. But nitrogen, on the other hand, we know that nitrogen has 1 non-bonding electron pair, and it's got 2 hydrogens attached to it. So now we've got 3 bonds on nitrogen, but we do have this non-bonding electron pair. So for a positively charged hydrogen ion, which again, remember, that is literally just a proton with no electrons, this hydrogen finds these 2 non-bonding electrons very attractive, and it wants to come over here and attach to it. So we end up with this ion right here, and this is going to have, let's see, let me go ahead and draw it and we'll talk about its charge. And this is going to become an ion with a positive charge because we've added a proton that had no electrons on it. And so we're just adding a positive charge to this compound that was originally neutral. And so now it's got a positive charge, and this would be considered an ion. Okay? So again, remember, all you have to know how to do for the test is label acid base, conjugate base. This other stuff is extra information for those of you that had questions about it or were curious about it. And then this example down here is from the practice packet to kind of help you figure out where that acidic hydrogen is going to go in a compound like this. Okay? So write down your questions, and I'll see you guys in class.